There we go. Okay. Brief recollections from last time. Remember, with this critical nonlinearity inside of with sigma, I can carry it out a little more explicitly in an instant, just so you understand what it looks like. They know it was a body back 8 coming out. So if P is this vector, then this matrix is this guy minus that. Clifford multiplication by this standard self-rule form. What does it look like? Well, E1 goes to 1, E2 goes to I, E2 goes to J, E4 goes to K, K is I. This is 2I, so this is 2 times this matrix, which is minus I over 4 times that. In sigma of phi is this self-rule form. And then the norm square of this guy is 116 plus 1 plus 1, which is an 8. Yeah.
He's a section of.
If he's a section of S plus. And and well, that's eventually solvable. Just to make that a little more explicit. And then again, these are Seiberg-Witten equations. Also part of the curvature of the connection. So the spin structure gave us this line bundle, a connection, line bundle, spin structure. Anyway, and then the amazing thing about the Seiberg, one of the many amazing things, first amazing things, is very clean identity for the norm squared of the Seiberg-Witten operator. So we take the norm squared of this guy, then I get these two terms, which again this depends on just G and S. It's the C structure. And then on the right hand side, I get something manifestly non-negative and controls something like the L21 norm of phi, L2 norm of the curvature, and then this thing controls the L4 norm of phi. So yeah, but we'll come back to that in a minute. But then the remember this, it's gauge group. And of course, the components. So this is a group. Components are H1 of X with Z coefficients, and there's a that sits inside H1 of X with real coefficients. Torsion in here, so that's really a subgroup, and then I'm going to say, yeah, but there's a natural map from here to here. If I think of Indram homology, I get a map G. It's some Q to 1 over 2 pi I U inverse du, which is that's the pullback by U of the standard. Sorry. Okay, great. Now, this symmetry is, both a boon and an annoyance. Oh yeah, I'm sorry. I also got the notation. I think I used notation. There's space of this is the space of connections in the line bundle. Plus spin bundle, and then that's the domain of the Seiberg-Witten operator, and then there's a domain which is the sections. So the forms becomes sections of negative spinors. And yeah, so these terms have this map, and this map is equivariant. Remember, you had some dimensions, so it's slightly strange formula, which is forced by the fact that the action of you the spinners is scalar multiplication, and again, this is the connection in the determinant, so the action of this on the determinant by the square of u, and that explains that factor too. So very formally, I could rephrase if G were acting freely on this, then very formally, what the more geometric way to think about it is that if I take the quotient, so if I take the quotient of the Seiberg-Witten of the domain, the Seiberg configuration space by the action of the gauge group, I can think of the Seiberg-Witten map, Seiberg-Witten operator, as a section of a vector bundle. So linear space on which G acts. This is well, it's also be a linear space, but no matter G is acting here, we have an equivariant map, and then we can think of that as defining a section of a vector bundle. And that's a good analogy. You should think of this when we define the Seiberg-Witten invariants, you should think of them as being the Euler class of this vector bundle. So formally, this all in quotes because the action is not free, but formally, when we define them Seiberg-Witten invariants are the Euler class of this bundle. That's an infinite dimensional vector bundle over an infinite dimensional space. Defining the Euler class is not trivial. But it's the Seiberg-Witten, because in more other versions of gauge theory, the gauge group is sections of locally looks like maps with some more interestingly grouped. The story is much more complicated, but this is a very simple space. And if we assume, as we will henceforth, if we assume that V1 of x is 0, then well, G is just homotopy equivalent to the circle. There's only one component, and that homotopy equivalent to U1. I want to keep calling it U1 as the group U1. But anyway, what we're going to do now is so I want to replace this infinite dimensional quotient by a quotient by a finite dimensional group that carries exactly the same information. And to do that, we're going to need to slices for the action. So anyway, I've got some space, and so configuration space, and this gauge group is acting. And it's acting in a rather simple way. Where did I write down? Yeah, that. Well, it's acting in a very simple way on connection. It's just acting by translation. Right? And we can exploit that to simplify our life a great deal. It's acting in a more interesting way on the spinners, but this is either G orbits. And what we're going to do is, let's define S of A, which depends on, sorry. Yes. It's been so long since I've written that script, but that's it. This is the set. Well, I'm going to pick an A naught, and I'm going to require. I'm going to just look at the connections that differ from my reference connection A naught by a co-closed one form. So this is some reference connection. Okay, and well, what do we notice? If the kind of position under this assumption, for all A infinity, there exists a U in the gauge group such that and times the spinners. Yeah, there exists a U so that U dot A phi is in the slice. So pictorially, what we want to do is we're going to find a subspace of the space of the configuration space where almost it's the case that the orbits pass through uniquely. That won't quite be true, but it will have reduced it to a finite dimensional issue. And what's the proof? Well, what do we want to do? We want this equation to hold, and so what we need to find U such that U dot A minus A naught D star of that. They want this to be 0. What is this? This is D star. I know how this acts. Now I think write A as A as A naught plus B. Then this is A naught plus B minus U inverse BU minus A naught. So that's B star of B minus 2 A naught. Right. And but I assume but I covered up the B1 is 0. Because B1 is 0, I can write U as e to the if for some function f. And then this equation is 0 is equal to B star of B minus 2 D. So B star D Great. So I want to solve Laplacian f is a half d star b. I can do that. So there's this unique f up to constants. Solving this equation. Okay, great. What is that? So proposition is true, and you notice exactly that we can refine the conclusion, and if A in addition, we learned that if u dot A P and A P are both in this slice, then that implies that u must be e to the if for a constant, so u is a constant gauge transformation. U is in one a constant. Okay. Here. So now the other thing which has a similar proof, I won't go through it. So our little lemma, if I guess this proves correct. So let's call this U1 inside G is the stabilizer of the slice as a setwise. That's what this just proved. If I have two gauge transformations that I have two things which differ by a gauge transformation and they're in the slice. So that's great. That means that if I look at this quotient, it's identified with this quotient. Right? So I've gotten rid of part of the infinite dimensionality of my problem. I can just work with the slice and this U1 action. So that's what we're going to do. And now we're going to so how do we organize that nicely? Well, let's set up an extended version of this operator. So we're going to keep the same. Our domain is still going to be this slice, but the range we're going to modify to v hat. V hat is v, and then we're going to add to it, well, d star of one forms. Okay. And my extended Seiberg-Witten operator w hat what does it do to AV? Well, it just does SW of AV. That gives me some, sorry. And then I'm going to take V star of A minus A naught against fixing this reference connection once and for all. Okay.
So the domain just C. sorry, C. No, sorry. The domain is C, yeah. C. Um, right. So, yeah, so what does this do? So here, the symmetry group that of these equations are just the constant gauge transformations. Okay. So this study was just U1 angle variable. This part obviously kills off the symmetry under gauge transformation, but that was exactly this down. Right? Okay, so now yeah, so this slice business buys us another important thing. So now suppose we have an A, and we know that having A such that what? Well, we have an L2 bound on this and an L2 bound on we have this Hermitian connection in L, and we have an L2 bound on its curvature. That's natural from the energy identity, right? And then, well, our extended Seiberg-Witten operator is going to control this term, right? So I can just kind of add that to the, I can add it to both sides with the energy identity, right? Then B1 is 0. The point is that I get an L21 bound on this difference. And what's the point? So so the curvature of A is the curvature of the reference connection plus 2 dA. So you get this is fixed. So this bound implies this is fixed that dA is also bounded. So constant is determined by this bound. And so what we have is that both of these are uniformly bounded. And well, D plus D star not in one form to this is an elliptic operator. So if I have an L2 bound on its image, I get an L2 one bound on its on A. Well, provided I have an L2 bound on A. But I'm assuming that B1 is 0. So B1 equals 0 implies B plus B star is injective. So that means that A is L2 one bounded and it's bounded in fact some constant. Okay, go through the computation carefully. Is bounded by some constant times the L2 norm of F and then L2 norm of B star A. Okay. So okay. I'm not going to erase this because that's what we'll look at next. Now, now what we're going to do, so let me, however, specify things just one kind of it more. We'll call it few facts. So norms. So L2 norm I assume is kind of obvious what I mean by that, but we need an L2 one norm on it's actually it's minus, and what we should do. So it's, again, it's fixing this A naught, and you write the L2 one norm on phi. Its square by definition is the L2 norm of the covariant derivative with respect to this convention plus the L2 norm of phi itself. On going plus, but I'm going to end up one L2 one norm. The L2 one norm is, I take the L2 norm of the covariant derivative, which is it's a one form, so I can take the covariant derivative with respect to the Levy-Friedel connection. That's the notion of derivative I'm going to use, and plus L2 norm, and then we're also going to use the L4 norm and L2 norm of the LP norms. That's just integrate the appropriate power of whatever thing over the manifold. Okay. Okay. Now, we need a couple of crucial facts in dimension 4. So that's I should say. Where are we going? We're headed towards proving that this is a proper map. Okay. So, and we're going to use the energy identity. The energy identity is telling us lots of good stuff, but I need to say there we go. So yeah, all right. So we need to figure out, we're talking about smooth things. That's not where it's proper. It's going to be proper on the completion of these spaces with respect to these norms. Okay. But a little more about these norms in dimension 4, and the key fact that we're going to need is that if you have you have a function, it's L2 controls its L4. That's called Seiberg-Witten embedding. And in particular, so that it's a map for L2 functions, which forgets that they're L2 and just remembers their L4 norm. Therefore, there are also embeddings of LP1 in LP, the P less than 4. And the key thing is that this is compact. This is not a compact embedding. So remember, how many people remember what a compact operator is? Okay, for those of you who don't remember, I will tell you a compact operator. So a compact operator is an operator that takes bounded sequences to sequences that have strongly convergent subsequences. So it takes the unit ball in your Hilbert space, takes it to a pre-compact set. The closure of the image of the unit ball it is compact. Another important characterization. So the linear operator is compact if and only if this is compact. L takes bounded sequences, with convergent subsequences. And for weakly convergent sequences to the same kind of gadget. And it's important to note that if K is it is the set of compact operators, then this is the closure of finite rank operators. So you should think of compact operators, kind of loosely thinking about them, but one of the simplest generalizations of operators to an infinite dimensional space, the ones that are pretty much finite rank. Okay. Now, okay, good. Anything else I want to say? Okay, so all right, let me do this. Okay, so now what I'm going to do is define this guy to be the sorry. All right. Trying to be cute, failing miserably. Okay, what I want to say is that I'm going to introduce this notation, and what C1 as the LT1, well, yeah, it's A naught plus the L21 sections of the imaginary one forms. So connections, remember, is an affine space. Great. That means I can take my reference smooth connection and add to it now an L21 one form. And but of course that's not enough. I need the spinners, and I want L21 sections of X plus. L21 for us just means that I have these norms and I complete smooth functions with respect to these norms. Okay, and V0 of S is just all two sections of self-real forms plus negative spinners. Okay, so but now I think you see why this is a good thing to do. Then we'll see in a moment. We need to think about it tiny bit. All of this stuff is controlled. It's finite for elements of C1. Right? You need to think about it a tiny bit, but what I said there implies it. And well, we're controlling the L2 norm target. That all makes good sense. And so leave that equation up. All right. So yeah. All right. So let's note that if we have a feed in this L21 guy, then that implies that this guy's in L2. Well, wait. This guy is the invariant with respect to the reference connection times a difference term. Well, that's in L2 by definition. This guy is in L21. This guy is in L21. Both of these can get into L4, and then something in L4 times something in L4 is in L2. So this is a L2. That's good because that's what I want to control. What I've given myself as a definition is this guy, but I need that back. Yeah, and also notice that since phi is an L21, that implies that phi is an L4, and that implies that this the third term is fine. Okay, so yeah. So we can turn these things around. So proposition there exists a function from R plus to R plus, which is an increasing
um, such that um, um, yeah, so that A in L21 plus A minus A naught in L21 plus D in L21 is simply what the F of the two norm of the Seiberg-Witten extended Seiberg-Witten operator applied to apply to A and C, right? And that's you know, that's pretty clear. If I just run this argument backwards, I mean, if I have L control over L2 on the Seiberg-Witten operator, then what's the logic? If I have control over this guy, in particular, I have control over this guy, right? But because it's the extended Seiberg-Witten equation, I also have control over the L2 norm of B star A. So I have control over enough to get control over the L. This should be L21. L21 norm of this difference. Right. And once I have control over the L21 norm of the difference, then I can run this argument backwards. Now I know this is an L21. And sorry, I have to do it. Yeah. So this guy gives me L21, and this guy, with a little thought, this controls the L4 norm of phi. And if this is finite, then it must be the case that it's a little bit messier. That's why it's a function. But it controls the L4 norm of phi. Once I know the L21 norm of A and the L4 norm of phi, then and the L2 norm, and the L2 norm of this guy, I get the L2 norm of this guy. So this estimate follows. And now we are in a position to prove the properties. The extended Seiberg-Witten operator has on that from C1 of S to B0 of S. Properly. What's the proof? Well, so what we want to show, so if we have the sequence A and Pn such that this guy gives L2 conversion. And we want to prove that this guy is L2-1 conversion. And to show well, yeah. Okay, well, the first observation using this proposition is that it's less than or equal to some constant. It depends on
this ultra-normative sequence. So that implies that that exists a weakly convergent subsequence. So, actually, this weakly converges to some configuration, and but we know a little bit more so we also know that the convergence, maybe after passing to a further subsequence, we can assume it's strong in some LP for P less than, right, because L21 into LP is compact. So from that's really good, because that means that you have almost everywhere convergence pointwise. And you're just thinking, gosh, I wish I'd pay attention to my else. It should have. Okay, great. That tells us something about the let's see, yeah. So I should have said so this guy is strongly convergent. Something. That's our assumption, right? But because we know that we have some kind of strong convergence of A and phi n, so let's look at this term. Okay. Well, this is just linear in A. So this term weakly converges. The first guy weakly converges to FA because it's linear. This guy, it's nonlinear, but okay, I think of it in LP. It's converging strongly, so it's converging to sigma of phi. So we have strong convergence to something. We have weak convergence to this. I think these are equal. Okay, and now I think that the kingly magic of the energy identity really comes to fore here. How do you tell if a weakly convergent sequence is strongly convergent? Well, so once again, giving you the benefit of the doubt, recall that if we had X in sequence in a Hilbert space, Xn converges weakly to X, then Xn converges strongly to X if and only if the lim hints of the norm of Xn is equal to the norm of X. So remember, the basic example of a weakly convergent sequence is to take the L2 Hilbert space, and then you take the sequence of coordinate vectors. Right? That's a weakly convergent sequence. It's not strongly convergent. It weakly converges to 0. So the weak limit has a lower norm. Everything in the sequence has norm 1, but the weak limit has norm 0. And the characterization of when a weak limit is a strong limit, just that you don't lose any norm. What the proof is easy. So I will give it. Well, let's look at this difference. We're in a Hilbert space, so like this. And the same thing is true in a reflexive Banach space, but anyway. I write this like this, and this is that. And now, if I take the take a sequence that's achieving the lim inf, what I learned is that the lim, so passing to the limit, well, this by assumption converges to the norm of X, but this is a weakly convergent sequence. So this converges to the inner product of X with X. So this is equal to X to the which is famously 0. And it also shows you that the limit of X has to be smaller than the limit. Otherwise, this would be negative. Okay, so having noted that, now we might have to pass this in further subsequences, but now we go back to the energy identity. And what on the left-hand side, well, we're assuming we get convergence, right? That means when I go look at the right-hand side, the right-hand side, everything on the right-hand side is L2 bounded, so I can still pass through I can assume that all of the terms there are converging equally, but so what we learn is that the limit of the right-hand side, the energy identity, is equal to just what it says there. Okay, so that's great. That means that in fact, it must be the case that that those. So that implies that nothing, no norm could have dropped in this weak limit. So this must be strong. Phi n converges for the T and AN converges in, sorry, I should say FAN converges to FA and L2 strongly. No. Got it, no. And now, this implies that AN converges L2 strongly to A. This and this tell me that A not P and then converges to A not P strongly. So that's what we want to show. It's a proper map, right? And I mean, I just want to emphasize in some sense, I almost did nothing. I mean, we just stared at that equation for a really, really, really long time, and it just gave us what we want. Right? And if you look, I mean, there's a proof in my book with Fredholm, there's a proof like this. If you look at the proofs, earlier proofs, they involve also beautiful arguments that involve maximum principal argument to get control over C0 norm of the spinner and stuff, but it's just the equations, just that energy and it's necessary. Okay, great. Well, the next thing to show, which we'll do in the next lecture, is that this extended Seiberg-Witten operator is proper, and the next theorem is that it's the Fredholm map. So I still have 3 minutes. Fredholm operator. Recall. Okay, then. Okay, now, let's solve that. From H1 to H2 is Fredholm sequence. If and only if this is a bounded object here. Actually, let's map it from H1 to H0. Bounded if and only if the kernel of F and kernel are finite dimension. Usually, many authors assume that as part of the definition that it's that closed range. That's actually the consequence of finite dimensional covariance. However, usually when you prove an operator is Fredholm, first you prove that it has closed range, then you prove that it has finite dimensional covariance. But as a definition, that's what you need. So then, like we saw before, these guys have an index, which is the dimension of the web minus the dimension of the kernel web. What else? Yeah. So you should think of Fredholm operators as the kind of dual idea to a compact operator. Compact operators are essentially finite rank. Fredholm operators are essentially isomorphisms. So they're kind of live in opposite universe. Compact operators are a closed subspace of operators. The set of Fredholm operators H0 is open. It's well, quite beautifully for Hilbert spaces. In fact, they model Z times B. I'm thinking here in this story, the relevant thing is real operators, but they're this is a model for the classifying space for real cases in that case. So there's lots of interesting topology, compact operators, obviously not. Yeah, what it means for a map to be Fredholm is if its differential for every point in here is a Fredholm map. So we'll discuss that
In the next lecture.